Well, I don't know about fun, but all right. Well, I guess we will get started then. Can you see my screen?
Yeah.
Let's see. I have to
I see
move
the
some
day
stuff
zero.
around so I can see the chat. You enjoy suffering? That's good. That's important. Okay. Kiwi, you can go ahead and start recording if you want. Okay. So, welcome to day zero. So today's mostly going to be going over the syllabus and then a little bit about assembly as well. So first, my question to you, what do you guys consider reverse engineering? Con. Or while he's typing, Stephen, you can also say, what do you consider reverse engineering?
Getting maybe a compiled piece of software or obfuscated software and sort of working backwards to try to figure out, what the source code might have looked like or what the functionality is supposed to be.
Okay. Yeah. So Con, I see that you're talking about assembly. However, reverse engineering can also be stuff with firmware. It can be hardware stuff. So the official definition of what is reverse engineering is it's the process of taking a piece of software or hardware, not just software, and analyzing its functions and information flow so that its functionality and behavior can be understood. However, I see reverse engineering more as finding a piece of hay in a needle stack. Whoever just joined, could you maybe mute yourself if you're not talking? Okay, I don't know. Thank you. All right. So what are the benefits? Stephen, go ahead. Tell us what are the benefits of reverse engineering.
Well, if you're wanting to hack something, then knowing how it works is a big boon in that regard.
What about outside of hacking?
Darn. Outside of
Darn.
hacking, you might be trying to figure out what some piece of software does. Say if it's malware or something, and you're researching the malware to see what it does and how you might circumvent it. You could take it apart and reverse it.
Mm-hmm. So the main benefits I see are you can find vulnerabilities, you can discover trade secrets. If you have a different software that does something and you want to figure out how it does, right, then you can figure it out. You can see how malware behaves, and once you realize how it behaves a certain way, you can either undo the damage it did or stop it from doing the damage in the first place. You can patch programs to change the software behavior. So if you have a game and you want to hack the game, first you have to understand how it works so that you can change it, right? And then, as Kiwi said, sometimes you just want to satisfy your own curiosity. All right, so what do you guys think are the good qualities of good reverse engineer? Steven! You got to keep the video going. I know. Too much time on their hands? Yeah. Having a whole lot of patience, that's a good one. Especially, as I said earlier, it's finding a piece of hay in a needle stack is the true definition of reverse engineering. But yeah, so as you said, you need patience, you need persistence, you need curiosity, you have to have the ability to think outside the box, right? Because a lot of times, the solution to how it was manufactured can be something completely different, right? That's why a lot of CTFs have those issues where there's, the shortcut solutions, right? All right. So what do you need to know to be a good reverse engineer? You need a solid level of assembly. You really only need one assembly language because once you know one, it's basically like knowing C. Once you know C, you can basically figure out all the other programming languages. You also need at least one high-level language. I really recommend learning C for this, just because you have pointers there. If you know Python, you're not going to be able to figure out C. But if you know C, you're going to be able to figure out Python and probably not like it very much. You need a solid understanding of operating systems. So this is the actual operating system. This is file formats. This is system calls. This is everything to like Win API, right? Because if you know the operating system, that's how the program interacts with the actual computer. So for example, one of the first things that you might check for malware or something is you're going to check how it interacts with the system. You're going to see what syscalls it does. You're going to see if it writes to the system, and then from there you can figure out the rest. And then lastly, you're going to need good scripting skills. All right. So so the structure of the course is going to be mostly, we're going to discuss some topics. The first few weeks are going to be just the absolute basics. And normally when you're doing reverse engineering, you want to go really broad, but we're going to go really, really specific. We're going to start off with assembly, and then we're going to go into file formats, low-level things, and then we're going to start learning about the tools a bit more. And the reason why we're doing that is because a lot of times people just know how to reverse something with a tool, but they don't actually understand what the tool does. So the course is going to teach you, how to actually really focus and know all the components that go into reverse engineering. We're going to cover topics, everything from the different tools, so static analysis, dynamic analysis, using Z3 Python, using Anger. Then we're going to cover specific languages because sometimes you have to use certain tools for certain languages. So C#, Objective-C, Java, so that covers APKs and Android hacking as well. We're going to try reversing cryptographic algorithms. We're going to do like a WinAPI crash course. We're going to do some game hacking. We're going to write and reverse packers and cryptors, obfuscation techniques, anti-debugging. We're going to do some firmware hacking, and then at the end, you're also going to be writing your own disassembler and decompiler for Recurso, which is a programming language I wrote. So that's going to be like the final project to see if you actually understand all the components and are able to implement them as well. Are there any questions? Yeah, you might want to have the chat recorded just so people that can actually, if they're watching the video, they can see the questions. Yeah, so there's a lot of topics and I was planning it out and I was making, a sheet of all the topics, and it's going to be a lot, but we're going to give you a good crash course for it. So it's going to be roughly about 5 or 6 months, I feel like, is going to be everything. We're going to be doing all of this in 1 year. And the answer is yes. So he also asked, or said that he thought assembly took a bit to learn. We're not going to learn, you're not going to learn how to program in assembly. You're going to learn, how assembly works at a more like fundamental level, and you're going to be able to read assembly, right? Because you don't really need to write assembly too much. You just have to be able to recognize what's happening. Does that make sense, Con? Hello?
We hear you.
It seems like my whole internet crashed. So while that's restarting, I'm going to be on here answering questions. Can you guys hear me now?
Yes.
Okay. Where did it leave off?
I think we heard pretty much everything you said.
The screen share?
Yep.
All right, perfect. All right, so now we are going to shift over more towards assembly. So who here has worked with assembly and who here hasn't worked with assembly? Also, to all the people who have come in, I try to make the course as interactive as possible, so please do try to respond. And if you do write in chat a question, I'll try to repeat it as well. Right. So I am going to send you guys a file. So I made this like a reference thing that you guys can use. And let me send that over because I'm going to be going over it, but I'm also going to be using DOSBox a bit. Okay. But, this way that you guys can still see it. And then if you want, you can use DOSBox. I wrote this little program here. So what this program basically does is it's going to be to teach you assembly. So it's just this little assembly program for DOS, and whatever you put in here will then get printed as hex values. So whatever is an AX gets printed. And this is just to make it a bit easier to learn the actual program. So for those who want to follow along in the video, here is that program. Okay. You guys can still hear me?
Yep.
All right. So does anybody know what, do you know what general purpose registers are? Have you heard of those before? EAX, AX, H, AL, stuff like that? Yeah, okay. So what it basically is it's how assembly kind of stores the memory. So here's how it's split up. So RAX would be, this register, right? And then EAX is half of that, AX is half of that, AL is the second half. So bits 0 through 7 are AL, bits 8 through 15 are H, and then 16 through 31 EAX, and then, the rest is all RAX. So if you did, RAX ANDed with, 0xFF or something, you'd get that component. So let me show you guys how that works. So we have this nice little program here. And so what do you guys think will be output when I do this? Any guesses? I saw you were typing, Cons. There's no wrong answers. So I mean, you won't get in trouble or anything like that. So yeah, what do you think? Do you know what the H is for? Okay. Anybody have any guesses for why that H is there? Ooh. Yeah, it is hex. All right. So what I'm doing right now, if anybody's following along, this is compiling it to an object file, and then you link it like this. So you don't normally need an O. The O is because we have the A here, right? So that's just something that's done. Up your streaming quality. I can try. Let's see. No, I don't have Nitro. Okay. All right, so based on this, what do you think's gonna happen here? So this would be 1 byte, right? How many bits is a byte? 8. Okay. So we have two bytes, right? So based on this, if we're moving it into AX, what's going to be printed out? And then this is in that PDF I sent, if anybody wants it. Any guesses on what's going to be printed out? AB? You think AB is going to be printed out? All right, well, let's see. So we get A, B, C, and D, right? Because AX, right, this is 2 bytes. AX is 2 bytes. So A, B, C, D, right? So we're printing out AX, which is going to be both of those. So then let's say now we move CD is the lower byte. Yeah. So now we move AL, and we're going to move 12H into there. What do you think the output's going to be now? AX is 2 bytes. Yeah. So you see here. Can you guys see the PDF here that I'm showing?
Yeah, I see it fine.
Because AB is 1 byte, and so Conv asked if ABCD is 4, how can we store it? So AB is 1 byte and CD is another byte, right? So that's because of hex. Yes. So now we've moved 12, so it's 1, 2H. It's not actually 12. So we are moving that into AL, right? After we move this into AX. So what do you guys think the output's going to be? You see that AL is here. All right, so you think it's AB12? Also, for those following along, if you change a file, you have to rescan in DOSBox, and then you can just do that all over again. It's a bit annoying, but DOSBox is a good thing to use. Also, if you're ever going to go into, 236 assembly at State, they use DOSBox as well. So having it set up is going to be helpful. You were right, AB12, right? So now, let's see, we're going to move, also this can be lowercase or uppercase, whatever you want. So what would the output be now? Oh, we have 2 different answers. All right, let's see. It is 3412. So, Conv, does that make sense? So AH is here, right? So first we moved the 1, 2 into AL, and then we moved the 3, 4 into AH. And that's why it's printing AH, AL. Okay. So that's just like a rundown of how registers work a little bit, right? Are there any questions for this part? Someone's typing. Okay. So here I went through and I wrote how all the registers are divided. If you're interested, you can read through that. I'm not going to go over too much, but just so you can get a general feel. You can see some don't have, the 2 here. It just goes all the way down. And then, okay, so that's there if anybody wants it. So the next thing we're going to talk about is accumulators. So accumulators are mostly used for division and multiplication. Because what do you think is going to be the biggest problem for multiplication? If we multiply a byte and a byte. Overflow, right? Yeah, because if you multiply the max by the max, you're going to get another size that really doesn't fit, right? But what about division? What's an issue with integer division? Why can't you not just store it in one place? Yeah, exactly. Remainder is going to be an issue, right? Because we're operating with integers here. So, 4 divided by 3, you're going to get 1 and 1, right? But you have to store that somewhere. So accumulators are, kind of used. Well, accumulator is used for the AL, and then it's stored here as well. But so the accumulator is basically going to be the implied and the target for all the multiplication and division. So I'm going to give you a quick example because that probably doesn't make too much sense right now. So, also, just a quick question for anybody. What happens if you XOR a value with the value again? So if you XOR 1 and 1 or XOR 2 and 2. No, it does not flip the bits. Anybody else want to try to guess? Yep, it zeroes it out, right? So a lot of times you'll see that in binaries or assembly, people will use XOR to basically zero out a value. So we're going to do that here. The value should be 0, but sometimes it won't be, right? So we're going to start off with unsigned multiplication, okay? So first we're going to move, I'm just going to write it real quick and then I'll discuss it. Okay. So if anybody wants to get a hex calculator or something, they can try to predict what the value is going to be. This is mul, not. All right. Does anybody want to try to talk about what they think is happening here? So why do we only have CL for mul? Why don't we have the AL as well? Let me move this so that you can see this as well. Anybody want to try to guess? Yeah. So it's a register, but it's also an accumulator. It's not accumulator register, but so CL is just a lot of times used, as you can see here, and I have a typo there. It's the counter register. You use it for loops and loop iterations. You can use it basically just for a lot of things. It's just a habit, but most of the time you'll see CL used for something like this. So CL, how big is CL? How many bytes? 1, exactly. So which of these do you think we're going to use? There's a bit of a hint because we're using AL as well, right? But we're going to use this first column, right? So the first thing that we're going to do is we're going to move E2 into AL, right? Because that's our source. Then we're going to move 3E into CL because we're going to multiply whatever is here, so whatever's in this source, with whatever's in this source. So you can use this table for figuring it out. So if we use CX here, it would use AX. ECX would go into EAX multiplied together, right? So now, what did we say was the big issue earlier, user, with multiplication? You remember what you said? Yeah, exactly. So that's why we have to put it into a bigger destination, right? So if we have E2 and 3E, did anybody do the calculation to see what our output value is going to be? Thank you. And why is it going to be 36BE rather than F8BC? Stephen? No? Or he's typing? Okay. No. So this mul is 36BC. You're correct. But what's implied because it's mul and not imul? Okay, yeah. So whenever you see mul, that's going to be unsigned. So you're not going to see mul too much, honestly. If you're going to be in assembly, you're mostly going to see imul. If you're doing actual analysis for binaries. And then what do you guys think the output's going to be for this? I kind of gave it away earlier. Right, it's going to be F8BC, right? Because this one is a negative value, right? So mul is going to be signed, imul is going to be unsigned. Okay. So now this next one, oh yeah, yes, these are two's complement. Does everyone here know about two's complement and how that works? Okay, perfect. Perfect. Okay, so now we're going to do a 16-bit multiplication. So for the 16-bit multiplication, I want you guys to use both of these values are positive, so you don't have to worry about that. But use a hex calculator online and just figure out what the value is going to be. Because I want you guys to then tell me what's going to be in dx and what's going to be in ax. Okay? And if you Google hex calculator, you'll find it pretty easily. Did anybody get it yet? Stephen? Okay, so dx. So we have ax, right? And we have the cx, and then it all gets put into here. So do you think dx is going to be f50 or is ax going to be f50? Dx is going to be f50? All right, let's give it a try. Did I rescan already? No, I did not. This is the one thing I hate about DOSBox. Okay, so first we're going to be outputting ax, by the way, because we didn't move it into dx into ax. Ax is, I did not update that, did I? No, I did not save that. Well, good thing is we can move dx into there and see if we were right. All right, f50 was in dx. Good job, guys. Really good job. Does that make sense? I'm guessing since everyone got it right, that made sense. And does this table help at all? I tried making it in a way that would help. All right, awesome. All right, so next we have division. All right, division, you guys got a multiplication pretty easily. So you guys will probably get division pretty easily too. All right, so here we go. What is, so 64 is 100. 100 divided by 3. What's our quotient and what's our remainder there? Okay, so what is the output going to be? So which of these, which one of these do we use? Yeah. Yeah. Do we use this one, this one, this one, or this one? Okay, perfect. And why are we going from Really? Can you guys hear me? Test,
I can
test.
hear you, but
Does that help?
I see you
That helps.
lighting up on
Okay.
Discord, and it's but we can't hear you sometimes. There's a really big
Okay.
delay.
Is this better now? Can you guys hear me now?
I think it might be better.
Okay. It says I have full thing now. I think one of my roommates is playing video games, so that might be slowing down my internet quite a bit. Okay, so why are we going from a bigger one to a smaller one now? Exactly. Yeah. And I'm really happy, Cons, that you said that it's reverse multiplication, because that is how the processor does do it. Awesome. All right, so now, based on this, what is our output going to be then, once this is run? Give me the full hex output. Also, it's going to be 33 is 21 in hex, so you don't have to go find a calculator for that. Anyone, any guesses? Is it going to be 0, 1, 2, or 0, 1, 2, 1 or 2, 1, 0, 1? 2, 1, 0, 1 is what you think? Let's see. 0, 1, 2, 1. All right. So what do we put into each value, right? So AH is going to be the remainder. That's 0, 1, right? AL is going to be our quotient. That's the 2, 1. If we go back up here, we can see it's AH and then AL, right? Does that make sense, Con? Okay, perfect. All right, now let's try it for dx ax. But rather than me giving you the assembly this time, how do you think, or I'd like you to try to write a little snippet of assembly to multiply that, or do like a division here. And what I'd like you to divide is 0.364 by 64. Those are both hex values. I guess 0.30064. Hello?
I hear you.
Okay, you can hear me? Why are you confused?
Because the Hackpack email bot came up.
Yeah, I know, that was a bit. Yeah. Use the 0.30064 divided by 64. And then we just make Nasser edit all this later. So, how many bytes is 030064? User. Okay. So 3 bytes is how many bits? All right. So that means we can't use AX, right? We're going to have to use DX AX. All right, let's see. Can we trust his? We can trust his. You're not editing anything? Okay. So Steven said it's this. Let's see if this crashes my computer. Here's hoping. Yeah. Well, no. I know Steven's is right, which is why I'm running his first. All right. So yeah, so remember how here it was DX AX and it put the high bits in DX and the low bits in AX? Conv asked what register is DX AX. So it's DX for the high bits, AX for the low bits, right? So imagine DX is all the bits that are shifted over 16. So you see how here Stephen put 03 into DX and then 0064 into AX. So that means that DX AX becomes 03 and then 0064. Does that make sense? Okay. User's still typing, so I'll wait. No. So if you do 0064, it's going to move 00 into the AH and 64 into the AL. So I technically yes, but I mean, just it's the way it's written, basically. User had asked if move depends on NDNS, and Kav is asking also, do we just use the registers under encoding 0 for now? Not sure what the others. Okay, so these registers, as you can see, AX, AH, AL. So this is the accumulator. So this is what you want to use as the dividend here, and then the divisor is going to be something else. I'll go over when specific registers are used for specific things in a minute, but normally you're going to use AX, AH, AL for accumulator stuff. You're going to use CX, CH, CL for things like storing the values in real quick, or using, like if you do a loop, something like that, right? Does that make sense? Kind of? I wouldn't say they're optimized for specific tasks. Some of them you have to use for certain things, like AX you have to use for multiplication and division. It's a lot of just preference and standard mostly. But there are some where you have to use them that way. And then just because of the certain standards, a lot of times what's underneath does certain things certain ways. So certain flags are set or things like that. So then using a different register can actually mess you up a little bit. But in the end, you're not really going to be reversing much handwritten assembly. Hope you don't have to reverse much handwritten assembly because it's not fun. Assembly, you mainly just learn so that you can understand the underlying processes, how that works, right? So it's learn it and then hope you don't really have to use it again. Yeah. All right, well, let's run Stevens and let's see what happens. All right, congrats. However, Steven, what happens if we, or anybody else, what happens if we make our divisor really small. Any guesses, anyone? So we have this huge, huge number, right? I don't know what that is off the top of my head. But divided by 3, that's going to be greater than 255 times. So what's going to happen? We're going to have an overflow. Now we're just going to have a complete overflow user. And I will show you guys how awful that is. It's not fun, especially because of how it behaves. So remember I said it was basically like a reverse multiplication rather than like a true division. Also, am I roboting again? Hello, test.
No, you're fine.
Okay. So remember how I said it was basically a reverse multiplication? I said that was a very good point that you brought up, Con. All right. So one of the big issues is if the quotient is going to be bigger than what we want to store it in, we're not going to be able to keep track of it, and it's just going to keep on trying to go. So if we run this, it's just going to keep going, and we can't stop it. So it's problematic, but you're not really going to run into this other than if you're handwriting assembly. So if you're taking the assembly course at State at any point, this is not going to be fun for you because you're going to have to restart DOSBox 2. And let me do that real quick while you're typing. So it loops forever. So it's reverse multiplication, right? So it's basically increasing the basically like the quotient almost, right? However, it's going to keep increasing it. Okay, so if we have, so here our quotient is AL, right? So based on, you know how this works, we have AH and we have AL, right? So it's going to keep increasing AL each time it does like the multiplication to see if we can do another multiplication. So, it increases AL over and over and over. If it's greater than the value, we go one under, and then the remainder just goes into AH. However, if CX goes into DX, AX more times than there's space, and I guess this would be AX and DX. Let me make that example right. If it goes in there more times than DX has space for, it's just going to basically overflow, and then it's not going to increase anymore. So it's going to keep trying to increase that value, but it's not actually going to increase anything. So we just get stuck in a loop, basically. So that is an annoyance. Does that make sense to everyone, user as well? Okay, awesome. All right, so now, Con was asking about what the specific ones do. So I'm not going to go too into detail because I wrote them up. But CL is mainly used for operations. If you want to shift bits, so if I want to shift AX over 5 bits or something, I'd put 5 into CL and then call SHR with either CL or with the CL or SHL with the CL. You have the stack pointer. Do you guys know what the stack is? Yes, Con? Okay, perfect. You have ESI and EDI are mainly used for like string operations. And then ESI contains the source address, and EDI contains the destination address. So many times, or basically always, you have a constants pool, right? So you see up here, the constants are here. So assembly really shows like a good way. All programming languages work the same way. So C, Python, all of that, they're going to have this constant pool, right? And it's because, when they go down into the assembly, you can put small values like this, but you're not going to, have this repeating everywhere. So you're going to say this is, in this position. And then the source and destination basically helps. It's going to say we're getting it from this position and we're putting it into this position. For anything big, so strings, variables that get changed, so that's kind of how pointers work, floats, and then some languages do it for other components as well. Does that make sense? So kind of asked if the values are stored there and just moved from there when we want to do anything. I wouldn't really say moved so much as they're just kind of referenced. Some programming languages do it a bit differently, but it's either it might be like a copy. They're going to copy it, or they just literally just read at that memory address. But all programming languages are going to have that constants pool, unless somebody wrote this one little language or something. So like a equals 3. So 3 isn't a constant. So you could make it one if you really wanted to, but most, and we'll cover this next meeting, because next time we're going to go a little bit over how, so this is register-based assembly. There's also stack-based assembly, which does pushing and popping. So something like 3 would be like iconst 3, and that basically pushes 3 to the stack, while something like referencing the actual like the string or something would be like pointer to string or something like that. And then we know get it from here, while something like a 3 would just be popped right into the opcodes. So DB, so you're asking about like this actual part here? This whole line. Okay, so this is the data segment. So I'm calling this codes. That's the variable name. DB is just the type of data it is. So you're either going to see DB or DW a lot of times. DW is for like larger things. And then this is the actual string. And then you put into memory like this. This is just for assembly, so you're not going to have to worry about it too much. And then if I want to access it, I get codes, which is the pointer to the beginning of it. And then let's say I want to get 1, right? I'm going to do codes plus 1, and that gets me this value. If I do codes, just codes, I get 0. If I do codes plus 2, I get the 2. Let me move that back. And this is like basically a pointer. Exactly, yeah. So it's a pointer to a constant, right? And you're going to use those constants for bigger values. Small values, like a lot of ints, are just going to be hard-coded into those instructions a lot of times. Just because it's quicker to pop them in. While, if you had to copy an entire string every single time, it's going to create a lot of overhead, and it's going to make that the byte codes are going to be a lot longer. So that's why the programming languages have the constants pool. Yeah. Any other questions about that part of it? All right. So the next thing, EBP is going to be your base pointer. So that's just, points to the base of the stack frame. I'll talk more about that later. The last thing that's super important for assembly, at least register-based assembly, is going to be the flags. Have you guys done much with like the flags in assembly, or learned about them a good bit? No. Okay. Awesome. This is gonna be fun. Alright. So there's lots of different flags. Normally the one that's used a lot is going to be the 0 flag. So whenever you see like a conditional in a binary, a lot of times it's going to be using 0 flag. So it's going to be doing JZ or something like that, which is jump. I'll go through all those. But the flags are basically set during certain things. So if we got an overflow doing, the stupid division I was doing earlier, this flag would get set. If we subtract two values and they equal 0, the 0 flag would get set. If we compare two values and they're equal, the 0 flag, 0 flag would get set. If we do some sort of addition, multiplication, or addition, subtraction, and we have to carry, the carry flag set. And it basically gives you just like a snapshot of what the last operation did. How would overflow multiplication set the 0 flag? No, it doesn't set the 0 flag. It sets the overflow. Yeah, sorry. I might have just spoken too quickly. And users typing too. So in assembly, it's not too. So user asked, how would you actually divide large numbers with a small one? In assembly, it's kind of a pain. But there's a few tricks to do it. You can use the larger registers, right, because you have the bigger quotients. And then a lot of compilers will do other tricks as well. Because, like even when you're working with C, your int is only going to be 32 bits, right? And then, that's not very useful. So like a signed int is going to max out at 32,000. But with Python, you have something, the numbers have no max size. So it's really done in compilers a lot. So, and, over the years, they've gotten so optimized that they do it in lots of different ways, and they do it really fast and efficient. So I wouldn't worry too much about doing that in assembly. We're just doing like a quick crash course into assembly so that you can read assembly when you're decompiling something else or disassembling something. All right, no problem. All right, so then there's a lot of different jumps, as you can see, and most of them, check a flag. So like JZ checks if the jump is 0, which just checks if the 0 flag was set. JNC checks if it's not set. Most of the jumps that you're going to see in when you're decompiling or disassembling, especially C or C-based languages, are going to be checking the 0 flags. So a lot of times you're going to see something like test and then JZ. So we're running a bit low on time, so let me just give you guys one more quick example. And I'm just going to copy it over from my notes real quick rather than, okay. So based on this code, what do you think is going to happen here? Are we going to print out 0 or are we going to print out 1? Also, these are labels, and it's just something that jumped. So like if the condition's true, we jump to true. When we reach this point, we jump to done, stuff like that. Does that make sense how labels are used? Yeah, okay, perfect. So we move 1 into AH, we move 1 to AL, we subtract them. Are we going to output 1 or are we going to output 0? There's no way to output 0? Why do you say there's no way to output 0?
You don't have a jump to the false, so it's going to fall through into the true loop.
True. Very true. Nice catch. All right, now what do you guys think? If what is 0? Okay, so it's JZ, right? What is JZ here? What do we check? What flag? All right, so we're checking if ZF is equal to 1. If it's equal to 1, we're going to jump. Now, how does the 0 flag get set? I have to rescan this because Steven ruined my assembly. Okay, yeah. So if we're subtracting 1 and 1, what's going to happen? Conv. Okay. So let's give it a try. And our value is 1. All right, awesome. So then what if we do, 2 and 1? Okay. All right, and that gets set to 0. So we're at 7, which is perfect. That was exactly how long I thought it was going to take to go through that, which is a good sign. Thank you guys so much for participating. Nasser, you can turn off the recording, and then if you guys have any more questions, I can just answer them. We're going to finish going through assembly, go over things like stack-based rather than okay, you're going to keep recording. We're going to go over stack-based rather than register-based assembly, just because it's a bit different. Not too much though. So will the 0 flag get set to false once we do another operation that does not result in 0? Yeah. So the flags normally get set after every operation. Any other questions about this or anything that we talked about today, including what we're going to go over throughout the course? If you have anything that you'd like to see in the course, I'm going to send out a Google form in a bit, just asking what did you guys like the most, what was the most helpful, what wasn't so helpful, other than the bad internet connection from time to time. This is x86 assembly user. What do you mean specific instructions? Yeah, this is Intel. This is 8086. This is Intel x86. Yeah. So you're asking about the different syntaxes. We're actually not going to go over syntax too much. Conv, we're using MASM6 because I already had it installed from the course, and if you're going to take assembly here, that's the one you're going to have to install. I figured most people would already have it, and I had set up instructions already for it from the course as well. Yeah, I mean, there's going to be minor differences, but as I said, we're not too focused about the actual syntax here. We're more focused about how it works under the hood. How flags are set, how the registers are subdivided, all of that. Because if you run across some random instruction, you're going to be able to Google it, right? There's no way that in this course, especially if we do 1 or 2 days, that we can go over every bit of syntax. But if you understand, how the actual logic behind basics work, you're going to be able to Google it and you're going to be able to understand. And that's kind of how this course is going to be run. I'm going to, give you a crash course of how it works, and then you guys can figure out, or I'm going to show you why it works, and then you guys can kind of figure out more of the how it works and play around with it outside the course. I'll provide all of the little assembly snippets that I went over in class today as well. I'll send them to you guys, so you guys can mess around with that. And that's why I built this little file here. So you can, you can go through and you can try lots of different syntax. You can try lots of different, instructions and all of that, and then see how it outputs. So it's a little, playtest area for you guys.